Hello, I am Mengqing Yao. I will introduce our work NeIF, Generalizable Illumination Neural Radiance Fields with Implicit Feature Volume. Let's start with the introduction first. Neural radiance fields created a new field of computer vision called neural rendering. Its pipeline is shown in the figure. It establishes multiple rays based on the camera's posture and pixel points, and then collects information in the space by creating multiple sampling points on the established rays. Finally, the color of each ray is calculated through classic volume rendering and compared with the ground truth to obtain the final result. This is the idea behind the original neural radiance fields. However, the disadvantage of the original neural radiance fields is the lack of generalization. It can only perform test rendering on a single training scene, and cannot perform training and testing across scenes. To address this problem, NeIF proposed the idea of constructing cost volume. They propose a generic deep neural network that can reconstruct radiance fields from only 3 nearby input views via fast network inference. Their approach leverages plane-swept cost volumes for geometry-aware scene reasoning, and combines this with physically based volume rendering for neural radiance field reconstruction. Their approach can generalize across scenes and generate realistic view synthesis results using only 3 input images. Another disadvantage of the original neural radiance fields concerns scene reconstruction under unusual lighting conditions. In response to this problem, there are 2 works trying to solve it. The first work is low light NeIF. Its main idea is to regard the sampling point on the light as having a brightness control part and a basic color part. By enhancing the brightness control part, the basic color part does not move, so implement low light enhanced NeIF. The second work is Alith NeIF, which proposes the idea of treating dark illumination and overexposed illumination in space as the color of the original object blocked by dark particles and overexposed particles. By removing the 2 types of particles, low-level lighting is achieved. Effects of lighting enhancement and overexposure correction. However, these works did not achieve the generalization of lighting conditions. Therefore, we proposed generalizable illumination neural radiance fields with implicit feature volume. Our work enables new perspective synthesis for generalized illumination. The model inputs data with lighting conditions different from those during testing during training, and can successfully obtain results that have never been seen before during testing. First, we will explain the meaning of the physical functions used in our model. We used a tone mapping function to simulate the camera imaging process when modeling lighting. After the camera shutter captures the radiance of the scene and the scene exposure, the radiance is converted into a radiance. The tone mapping function, also known as the camera response function, is then used to apply the scene exposure to the captured irradiance to obtain the image on the display instrument. The process can be written as this first formula, which we simplify to get the second formula. Where C represents the color, F represents the tone mapping function, H represents the irradiance and delta T represents the exposure time captured by the shutter. Then we show the pipeline of our model. Our model is divided into 3 parts. Part A is the construction of the lighting feature volume, Part B is the construction of the tone mapping function just mentioned, and Part C is the classic volume rendering method. The main idea is that in each training iteration, 3 pieces of data with the same brightness are randomly used, 2 as the source view, 1 as the target view for the ground truth, and then one of the 2 source views is randomly selected as the reference view. By mapping the features of the source view to the reference view, the designed network obtains the feature volume, and allows the target view to sample in the obtained feature volume, by allowing the feature volume net to learn to fit the spatial illumination information under the unknown perspective. Input the obtained features into Part B, and at the same time input the exposure time corresponding to the data used in this iteration. In the designed network to fit the tone mapping function, the pixel color corresponding to the lighting is output. Perform volumetric rendering of color, and supervise the resulting rendering result with the target view. Next, I explain the details of our approach. The first step of our method is to construct feature volumes for geometric matching. We first pass the input source view E through an 8-layer 2D convolution network to obtain the feature map phi. Then we use the idea of a single mapping matrix in Formula 2 to rotate, and map the feature map from the source view to the reference view. For any 3D point X, in world space, given the intrinsic matrix K, the camera rotation R, and camera translation T, we consider the homographic warping as Formula 2. HIZ is the warping matrix from the source view I to the reference view at depth Z, and NREF is normal at the reference view, computed by the homography matrix. Each feature map Fi can be warped to the reference view by Formula 3. Where Fi, Z is the warped feature map at depth Z, and U, V represents a pixel location in the reference view. Then we leverage the variance around source views to compute the volume. At some arbitrary depth Z, the voxel centered at U, V, Z is computed by Formula 4. Where P indicates the implicit volume and the FM is the set of inputting views. We utilize a 3D IJCNN2024 to encode and decode an illumination implicit volume that consists of the voxel volume P to the properties used in the tone mapper. These processes are expressed by Formula 5, where X is the 3D point's position, D is the target view direction, and F denotes the volume feature. For brevity, the following are omitted from the formula. The first part of Z is used for encoding and the second part of Z is used for decoding. Secondly, drawing inspiration from the camera response function process, we aim to integrate exposure time as a significant factor in our approach. We use the tone mapper to transform the captured signal into the pixel value with the specific exposure time. After obtaining the feature volume, the next step is that sampling points along the rays emanating from the target view through the volume. These sampled points' positions, directions, and volume features are then fed into the tone mapper for further processing. As the three formulas on the right demonstrate, invert the tone mapping function. The X is the pixel passed through by the ray, and we take logarithms to both sides of it. In practice, we can easily obtain the exposure time delta t from EXIF files that contain metadata about photos, such as exposure time and focal length. Additionally, the RGB channels of images need to be tone mapped with different CRFs. Therefore, we divide the RGB channels into 3 different parts and use 3 MLPs to learn every channel's tone mapping process independently. Finally, we will show our experimental results. For our model, we designed 4 experiments. The first is to compare the effects of original NeIF, HDR NeIF and MVS NeIF under the same training data. It can be clearly seen that the original NeIF cannot achieve the goal of illumination generalization. HDR NeIF has a large number of artifacts, while the clarity of MVS NeIF is far inferior to our model. We show our evaluation metrics on the right. All of our metrics are better than the comparison methods. The second experiment demonstrates the illumination generalization ability of our model. Qualitative results of our novel illumination views on synthetic scenes. The brightness increases sequentially from left to right, and there are new perspectives of different target brightness generated by our method. Finally, we designed 2 ablation experiments. The first ablation experiment is about the use of the loss function. In our experiments we noticed that the MSE loss has the disadvantages of losing control of the pixel brightness, and imbalance of the weights of dark pixels and bright pixels. Therefore we chose the inverse tone loss, which can balance the weights and control overall exposure within an appropriate range. We compared the experimental effects of the 2 loss functions and the metrics are presented in table. It can be seen that the brightness of A is closer to ground truth than the brightness of B. We test different target exposure times, and the results show that the effects of the inverse tone loss are better than that of MSE loss. The second ablation experiment is about the details of the training data set. In order to achieve the best results, we tried using different numbers of training scenes and different numbers of exposure times. Finally, we found that when the scene data is 3 scenes or more and the number of exposure times is 4, good results are achieved. In this paper, we propose a novel method to render novel illumination views from a set of views with different illumination. Thanks.